Good evening, everybody, and welcome to our, I believe our third, one, two, three, fourth in our 25-26 Cygnus Lecture Series, a program that began during COVID to help keep keep our audience engaged, keep science and STEM education going. As opposed to our normal in-person talks that we've done and we're continuing to do now to a certain extent. The Cygnus series has become very, very popular, as you can see tonight, based on our enrollment, and allows really not just national or regional, but in some cases international attendance for these talks. So we are happy to be providing this program, and we'll continue to do that. I'll show you a little bit of the what's yet to come in the series for the rest of the year in a little while. But let me first take you on a little bit of a 20,000-foot view of who we are as the Adirondack Sky Center and Observatory. And if I forgot to mention it before, my name is Seth McGowan. I'm the president of the Adirondack Sky Center and Observatory, and I'm proud to hold that position. We are located in Tupper Lake, and I see some of you have recently visited the Sky Center, which is very exciting on a clear night. We've got great viewing, but you can see where we're located, right in the middle of the Adirondack Park there, a very, very dark area in the northeast. And we have the ring of fire or the ring of light, light pollution, all around us. And our visitors come from all over the country, but in particular on any given night when we announce that we're going to be opening for stargazing, we've got an audience from the major cities as well as locally within the Adirondack Park. So that's always it's a nice boost. We're a great add to the region, and we're happy to be here right in the middle. We really our goal is essentially to demystify the universe for folks by just making it very hands-on, exciting. We want people to think about things a little bit differently, and we want people to feel comfortable in their own universe, which is really where we all are. Our goal is to make the universe accessible to everybody. We demystify. We don't want everybody to feel like you need to have an advanced degree in astrophysics to feel comfortable in looking up and understanding what's going on up there. Not true at all. As I've told you before, if you've been to these talks, I'm a retired superintendent of schools here in Tupper Lake. I was the band director here in Tupper Lake for many years, and that's my background. Never took an astronomy course in my life, and here I am. So we refer to it as the wilderness above, coined by our longtime board member, Eileen O'Donoghue, meaning that really from the tree line up, that's where everything started. We tend to think of the wilderness as the forest around us, which is absolutely true. But all of the atoms, all of the particles, everything that is in those trees, that is in the water, in the clothing we wear, in the computers you're looking at right now, everything started in a star someplace, and that's the beauty of the wilderness above. We have an office at 68 Park Street, and we do our main office hours there are just general business hours during weekdays. We do programs there, after school programs there. And we have other things that go on. Right now, we have an art installation called Universal Visions, and that's the result of our astrophotography conference. I'll talk a little bit about that too. We've got a number of programs that we do. Cygnus Series is just one portion of that, but from public, private observing, large celestial events. For example, if there happens to be an eclipse in the area, you may have heard that we plan and coordinate those with the greater universe, so we know when they're coming. Um, we have a portable planetarium. We do astrophotography conferences. We do student outreach, visiting schools all over the Adirondacks and so forth. STEM related too, not just necessarily astronomy, but all STEM related as we're asked to do. We have after school programs. This is a telescope making class that we did a few years ago for parents and their kids. This girl used that telescope that she made from looks like a toilet paper roll or a paper towel roll to view the rings of Saturn at our observatory that night. It was really exciting. We have a new program thanks to Simon called Cosmic Explorers, and the first installment of that program was literally rocket making for adolescents and younger this summer. Great success. Launched a ton of rockets, taught kids about propulsion, about chemistry, all sorts of stuff. So it was really very successful, and we're uh, hosting something coming up on coding. So we're excited about that. We have our all new digital star lab, which is actually not that new anymore. I should probably take the new out of it, but that's the thing that travels from school to school, and we give students the opportunity to be inside a planetarium during the school day. And sometimes, depending on the size of the school, we can get the entire school in there from pre-K through 12th graders in there and have an experience in there in a single day. In larger schools, sometimes we're parked there for a week, and we just literally go through the whole student body, and all aligned with New York State learning standards, with the next generation science standards, and so forth. So we work with the teachers to customize the experiences for the students. Our keystone event is our annual astrophotography conference. It's a very immersive experience where we have folks bring their equipment, bring their cameras, bring their telescopes, bring their computers to us so we can teach them how to get to the very next level of astrophotography, which is not a point and shoot kind of a hobby. It's very technical, very expensive, time consuming, frustrating. It feels like there's nothing good that comes out of it until you get that picture. And then I can say there's hardly anything more satisfying than that in, in, in my experience in astronomy. As a result of that, we've hosted our first exhibition of the photography from our own students right in our office on Park Street, and that is called Universal Visions. And again, these are all images. They're large images, 3 feet by 4 feet in some cases, high resolution, professionally printed and mounted gallery style. So you feel like you're walking into an art gallery, and you're seeing objects in our universe that you would never in a million years necessarily think that were up there, that were available to us, but all taken from right here in Tupper Lake with our own folks. So we're excited about that. If you're in the neighborhood, please stop by and check that out. Free to the public. Here's our Star Lab. We do weekly showings of different programs professionally made for a planetarium experience. And those rotate from month to month. We've done things from, talking about the original Apollo missions to things that take you out to the very edge of the universe and so forth. So this month's presentation is called Sunstruck, about what comes at us from the sun. So as scary as it is, when there's little kids, sometimes we have to talk them down off the excitement wall, because some of it can feel a little bit scary until you realize that we do have an atmosphere and a magnetosphere that protects us from all of that stuff for the most part. Our online lecture series, which you're here for tonight, is a series that will run through 2026, and then we'll kick it up again in the fall of 2026 and have another set of programs. And here's what we have to look forward to. Tonight, we were looking forward to Simon and his cosmology and gravitational waves, and that will be coming shortly. We do private stargazing parties. If you have a birthday party that you're looking for something special for somebody, or an anniversary, or a class reunion, and you want to invite some people, you can quote unquote rent the observatory for a night, and you get along with that all of the telescopes, but you also get an astronomer. One of us will help guide you through the night sky. It's a lot of fun, and literally there's no use your imagination. We can host anything. Uh, I've got coming up in a couple of weeks. A guy is going to propose to his girlfriend, and that's always very exciting. We've had that before. So if you've got a special event that you're interested, please give us a ring. We do our public observing programs. This is the way we start out on the back veranda, where we explain what we're going to be looking at through the telescopes, which are inside of the roll off roof observatory. And you can see that 4,000-pound roof rolls right back off and exposes all of the telescopes in the building. And there's four permanently mounted high power telescopes that you can see objects, 58 million light years away or more. So these are not things that you can just pick up at your local Kmart. Our big news, of course, is that we are hoping to add to our roll off roof observatory an actual planetarium, which is exciting because we'll be one of the few places in the country where there's an observatory and a planetarium. You know, of course, that most of the time a planetarium is in the middle of a city, New York, Philadelphia, Boston, and so forth. And a planetarium or an observatory is typically, up in a high elevation on a mountain someplace. Well, it turns out that's kind of where we are already. And we have enough folks in the area who come from on a tourist basis, and so adding a planetarium to that roll off roof would be a great addition, and we'd be one of the few sites that held both. On our property now is about 6 acres. The roll off roof observatory there is in blue. The planetarium is the next phase, and that would be this section. So it'll be literally on the same exact property, and that would be a daytime or evening experience. Same sort of a thing. It will be also available for special events. It'll have actually a large event room in it, and you can see, in addition to the planetarium room itself, there's a large function area also for weddings or anything. People are getting married in planetariums now, so we hope to be offering that experience pretty soon. The dome itself is traditional, as you would imagine. If you've been to a planetarium in the past, it will be the state of the art, the newest in HD and 8K and digital uh, video and sound. So it's going to be state of the art technology, and just sort of a rendering of what it is planned to look like. And this is sort of the idea. So with that, we're in sort of the dark sky area. So as I mentioned previously, we have an initiative to set Tupper Lake as a dark sky community. And again, being in the middle of the Adirondack Park, we have access to the darkness already. And the International Dark Sky Association, or now the Dark Sky International, has our initial application for designating us as a dark sky community. And we're working with the village and the town and the community to put that in place. That'll take a little while. It's not something that happens overnight, but eventually from there, our goal really is to move outward from our central location in the Adirondack Park, and maybe move to another community nearby, and then eventually capture all of the communities and become a dark sky reserve, the 6 million acres of the Adirondack Park. And I can't say enough of what a great boost to regional economic development, to our status in New York State, in the Northeast, and really
Mindset,
even
stop talking.
in the in the country. So, on actually, a friend of ours, Jimmy Webster, is on our call tonight. He works down in Tom's River on the same sort of thing, so we look to him for some help. So that's sort of it. That's kind of
Like
what we're
fucking
working on,
God.
who we're working with, and what we're working on. and really excited about all of the things we're doing. So if you're interested in finding out more about us or getting on our mailing list, visit our website. You'll get updated mailings and more information about us as we go. So that's us. Now, the real feature tonight is our featured guest, and I'm proud to say one of our own, Simon Thill, who is our uh, astronomy outreach coordinator and does a lot of the programs, but also has some extensive background in cosmology. So he was going to bring that to us tonight. And I'll just remind everybody, if your microphones aren't muted, please do that at this point. If you have questions, put them in the chat. We may stop along the way to answer some of those questions, but otherwise, we'll take questions at the end, and this video will be available later on down the road on our YouTube channel. So with that, Simon, our cosmologist, please take us on our adventure for tonight.
Hey everybody, it's really great to be here. I will be talking about cosmic waves. Um, and so the title of my talk relates to the fact that waves and the physics behind the study of waves is really the study of astronomy. This will all make sense in a second. So I majored in physics in college. And during your first year of physics, you take a lot of introductory courses that are really just basic simple mechanics. What happens when two things crash into each other, or what happens when you throw something. Uh, your sophomore year, so your second year in physics, is when you start to take the maybe not advanced, but the upper level classes. And I was really excited for these classes, and I was really excited to learn more. And the first class that I took as a sophomore was I read it on the syllabus. It was or the transcript, the registrar requirements. The first class you have to take is called Waves and Oscillations. And I went up to an upperclassman friend of mine to ask, what's this class about? Like, are we learning about like surfing, water waves, waves in the ocean, tidal waves? What? And he said, "Oh, that class is about pendulums. You'll be studying pendulums." I'm like, "Okay. So what are we going to do the second day? Is pendulums it?" And yes, pendulums was pretty much the only thing that we studied in that entire class. First half of the class was pendulums, so those things in grandfather clocks, just simple back and forth motion. Then the second half of that class, we graduated to the upper level and we studied what happens when you vibrate a string. So if you have just like a guitar string. What happens when you pluck a guitar string? How does that string vibrate? And I was really confused. I didn't know, why are we talking about pendulums? Why are we talking about waves on a string? Maybe you guys are all coming to this talk wondering, why are we talking about waves when we should be talking about astronomy? And what I learned from this class is that the reason that waves and oscillations are so important to study is because they are everywhere, specifically in astronomy. This talk is divided into two sections. So, in the first section, are we talking about how we use waves as a tool to study the world around us? And in the second section, I'll be talking about how waves give structure to the world around us on the smallest scales and the largest scales. Um, and yes, the thesis of my talk is that even though it doesn't look like it, the study of astronomy is really the study of waves, and really the study of physics. It's really hard to find any topic, any research topic in physics or astronomy that doesn't involve waves in some form. Um, Now to start, I'd like to advance my slide. Here we go. Um, to start, I'm just putting it out there. What is a wave? the type of wave that we are probably all most familiar with is a sound wave. Um, they're all around us. We hear them constantly. They're how you're listening to me now. But we know these probably best from music. So a classic example is this wave is that's traveling along a violin bowstring. So whenever you pluck any instrument, any guitar, any stringed instrument, but I mean there are strings in a piano, uh, all of these instruments, they operate in the same way. You have the string and you send a propagation down it. And that's what you're seeing in this image here. And what physically happens is it's really as simple as the string bashes up against the air molecules all around it. That's I mean, there's a little bit more details that go on when you really get into the study of acoustics, but at a fundamental level, what's happening is you're just slamming these air molecules into each other. And that's what is shown in this animation on the right. You take all of these particles, you line them up, and you get these pulses. So these pulses, these areas of really high pressure where the molecules are really tightly packed, and these areas of low pressure where they're spread out, and those propagate through a medium. So this is in the rest of my talk, I'm going to be talking about cosmic waves. So I'm going to be talking about pretty abstract concepts like gravitational waves, electromagnetic waves, how these are used, how the electron fields and have those behave as waves. Those are very advanced concepts, but you can just remember whenever I say waves, it's the exact same physics, it's the exact same mechanism as just the sound that you are listening to right now. Um, and then sound is just probably the most familiar type of wave that we are used to, accustomed to hearing. But then, of course, waves on the ocean, tidal waves, those are all other types of waves that also count, and including this jello. So this jello has ripples traveling through it. They're you can kind of think of it as like they're similar to like waves on an ocean, those ripples traveling through an ocean, and they make it wiggle, they make it jiggle. Wiggling and jiggling are the scientific terms that, no, I'm just kidding. They're not really scientific terms. But the rest of my talk will be a little bit more abstract, a little bit higher level. But at the end of the day, it's the same physics as jello wiggling. It's the same physics as music in your ears. So yeah, I mentioned this earlier. I'm going to start by talking about how we use light to learn about the universe around us. That will be the first half. And then in the second half, I'm going to be talking about how waves and the physics of waves give structure to the universe. And you'll see what I mean by structure. Um, and there's a little hint on the structure of an atom and how that relates to the structure of the universe as a whole. Um, Now, first off, we're talking about information. So it's very difficult to be an astronomer. You know, if you were a biologist and you wanted to study chimpanzees, you could go out into the rainforest and you could interact with chimpanzees and you could run experiments on them. You could put them in situations, you could put them in different scenarios, and you could collect data hands-on. If you were a geologist, same thing. You could go into your backyard and break open rocks and see what their structure is inside. See what are these rocks made out of. Astronomy is fundamentally different. We are thousands to millions to billions of light years away from the objects that we study. If we want to study the composition of a star, what is this star made out of? You can't just go to it and rip it open and look inside. Uh, Likewise, if you want to see how do the planets in different solar systems, how do they uh, interact? What behaviors do they exhibit? You can't just run simple experiments on them. Um, the only thing that we can do is look at these objects. So for millennia, the only tool that we had available to us to learn about the universe surrounding us was the light. So light, I'll talk about this in a second, but light is a wave. That's the first wave, that cosmic wave, that we are going to be talking about. Um, and this wave can propagate through space. So if there's a star millions of light years away, we will never be able to touch it, but we can learn about it because, excuse me, this light wave can travel those vast distances to us. So light is really important in astronomy. Um, so I'm going to take a minute here to talk about what light actually is and then how we use it to learn more about the stars in the universe around us. All right. I have a quick video. Just before I play this video, um, I'm going to make a quick note. So when you talk about a wave, you often talk about it as propagating through a medium. So sound waves are, like that animation I showed, those are regions of high compression and low compression. And it's literally the air molecules around us. So it's propagating through air. That's why sound can't travel in a vacuum. If there's no air, there's no medium for it to travel through. Sound needs to travel, or sound is these air molecules bumping up against each other. So light, the light that's all around us, is also a wave, and it's a wave in the electromagnetic spectrum. So you might have heard of these forces. There's this electric force. So if you have a charged object, say you have an electron has a negative charge, and uh, that charge is mediated by an electric field. So I'm going to show an animation of what happens when you take an electric charge and you shake it up and down. Okay, perfect. So in the center of the view, you see an orange ball. I'm going to play this again. That's an electron, so it's negatively charged. And as you wiggle it up and down, you see these arrows coming off of it. Sorry, the animation is so short. I'm going to play it one more time. These arrows represent the strength and the direction of the electromagnetic field. So the electromagnetic field is something that if you've used a compass, you're familiar with it. When you use a compass, that the arrow of the compass aligns with the magnetic field. If you had a compass here, okay, and if this was the magnetic component of the field, the compass would align with these arrows. And as you can see, these they propagate outwards, and they're a propagation just like a sound wave. All right. So what can we use these for? So light waves are produced by these wiggling atoms, and they are produced by everything in the universe that you can see, pretty much. So a distant star will produce these light waves, and it turns out that the type of light wave they produce. So here, there are these all light waves travel at the same speed, the speed of light, but there are differences in the wavelength of light. So some will have shorter distances between these regions where uh, the arrows are pointing up versus down. The wavelength corresponds to how far apart those distances are. So longer wavelength versus shorter wavelength. That's not as important. The real takeaway message is that um, different phenomena produce different types of light. So, for example, stars with different surface temperatures will produce different types of light, and stars that are the color of light will be different. And stars that are far away, the light that reaches us will be slightly dimmer than stars that are closer. You're all familiar with that effect. And there's another effect that's really interesting is that if a star is moving away from us or moving towards us, its light will be stretched, or so its wavelength will be slightly stretched or increased. And again, the take-home message is so just from studying a few properties of light, basically its wavelength, we can learn the temperature of a star, we can learn how far away it is with some caveats, and we can learn if it's traveling towards us, if it's traveling away from us. And by studying every star in the night sky, we can learn a lot through just light. Um, okay. Uh, And that's exactly what we've done. So we've built telescopes and all these tools and all these instruments to supplement our eyes and allow us to learn more about the universe by using just light. Now, I'm going to talk about another type of wave that is also used to learn about the universe around us. So on the left, we have a diagram of an electric charge. So this negative Q, Q is the symbol for charge. I don't know why it's not C. They just chose Q. But if you have a negative charge, so for an example, an electron, this could be an electron, it will have an electric field around us, and that's represented by all of these arrows pointed towards it. Um, and if you're one, and that is that video that we just watched. So the oscillating charge up and down and the electric field lines that there were little arrows pointing up and down that switched. That's that video that we just watched. So if you take a charged particle, shake it up and down, it will create a ripple in this electric field that travels outward, and that is light. That's an electromagnetic wave, that's light. All right. In parallel to that, on the right-hand side, we have a particle that doesn't have a charge, but it has a mass. So particles with mass, protons, neutrons, electrons, these are all very small particles that have very, very, very small masses. But there are also very large objects with mass. So for instance, the Earth is a very large object, and it has a very large amount of mass. Even more massive is the sun, or a neutron star, or a really huge massive star, or for example, a black hole, which is basically the most massive objects that you can get in the universe. So all of these objects have a mass, and they also have so gravity is a force, just like the electric force, and so just like the electric force, there's a field around it. So these particles or these objects have a gravitational field pointing inwards towards them. So electric force, electric particle, charged particle, electric field, gravitational force, you have a particle or an object with mass, and you have a gravitational field. There are a lot of similarities. There's another similarity. So when you shake an electric field, you get a wave traveling in this. I think I misspoke. When you shake a particle or an object with charge, you get a wave traveling through its electric field. Similarly, when you shake an object with mass, you get a wave traveling through its gravitational field. These are known as gravitational waves. Gravitational waves were theorized by Albert Einstein in, I believe it was 1916. And as soon as he theorized them, people were like, we really want to study these. We really, really, really want to detect these. And they've been searching for them ever since. And these gravitational waves are very, very small. They're very, very difficult to detect directly. So they weren't directly detected until 100 years later, in 2015. So just 10 years ago, was the first direct detection of a gravitational wave. Um, and it was really exciting. It was really the start of gravitational wave astronomy. Um, and well, we can use gravitational waves to learn a lot about our universe. So, I mentioned you create an electromagnetic wave, a light wave, by shaking a charged particle. But what happens if you have, and the same thing happens if you shake an object with a lot of mass. So if you shake a black hole, shake it up and down, you get a gravitational wave. It's obviously it's a little funny to imagine shaking a black hole. You can't actually shake a black hole. But what happens quite often is that there will be two black holes or two objects that orbit around each other. So the Earth and the Sun. The Earth and the Sun orbit around each other. There are also many other star systems where two stars orbit around each other. Or there could be this star system. This animation shows two black holes orbiting around each other. And as they orbit around each other, as you can kind of see in the middle, they effectively are shaken. They effectively go back and forth. It's as if they're wiggling. Um, so this wiggling produces these gravitational waves. So which you can see as these like kind of ripples in a fabric that are propagating out. So we have light waves, which tell us a lot about specifically stars. Um, but really, yeah, specifically stars. Stars are the main thing that produce light in the universe that we can see. Um, and then we have gravitational waves. Okay, so I mentioned this before. We've been looking at the stars, we've been looking at the night sky for thousands of years, and we've only been able to use the light that they produce to learn about them. And using that light, we've learned so much. Now, it's as if we've opened up a new window, a new view of the night sky. We can effectively see more. So now that we can also, again, we can't really see gravitational waves because they're not light waves, but they're very analogous. So now that we can quote unquote see gravitational waves, we can learn a lot about the universe around us. Specifically, gravitational waves are produced by these inspiraling binaries. So we've learned a lot about how the most massive objects in our universe interact. So what happens, how do two black holes interact with each other? Um, how do they orbit? And eventually, as black holes orbit around each other, they eventually get closer and closer, and eventually they merge and create an even larger black hole. And that is one of the most violent, extreme events in our universe. Um, and it's worth mentioning. So black holes are black; they don't emit light. Um, so there would be really no way to study these interactions if it were not for the gravitational waves that they produced. Um, and gravitational and black holes are really important to study. They tell us a lot about because they're so massive, they influence a lot of things. Their force will can shape the structure of entire galaxies. Um, so by studying gravitational waves, we can study these huge, monumental, very extreme events in our universe. And we can also study a lot more. So this concludes the first half of the talk. I'm going to go on and talk about the structure, how waves influence the structure of the universe. But first, I just want to ask the question, how are we doing? Uh, I hope all that is clear. But if anybody has any quick clarifying questions, burning questions that they'd like to start uh, to ask before we move on, be happy to take a few. And while you think, I'm going to drink some water. Okay, great. I don't see any questions in the chat. So hopefully that was clear. Okay. All right. Okay. I have roughly 15 minutes, and I'm now going to talk about structure of our universe. This is a little bit more theoretical, but the main thrust of my argument is it might not be obvious, but waves determine the structure of atoms. So on the smallest scale, the structure of the smallest objects in the universe, like atoms, are determined by the physics of waves. So the same physics that gives rise to sound, that gives rise to music, the same physics that make, a major chord sound nice, uh, they give rise to the structure of atoms. I'll explain why in a second. And then you might be asking yourself, well, why are we talking about atoms? Shouldn't we be talking about the universe? Well, this is the crazy bit. I still can't believe it. But the structure of atoms actually influences the structure of the entire universe. So what do I mean by structure of the universe? You'll see more in a second. But basically the large scale distribution of galaxies. So if you zoom out, if you zoom out on scales of like 300 million light years or more, how are galaxies arranged? How are they distributed throughout the cosmos? The answer to that question is dependent on the structure of atoms, and they are both answered by the physics of waves. Okay, I will explain all of that in just a second. So first of all, the structure of an atom. So this is a really common, this is a simplified view of an atom. This is maybe what you would see in a middle school classroom. I think I learned about atoms in seventh grade, and this is kind of the diorama that they presented us with. Um, these black or grayish spheres that are electrons, so they're negatively charged. These red spheres in the middle are uh, protons. Wow, sorry, I forgot that word. Are protons, so they're positively charged. And then the blue spheres are neutrons, so they have zero charge. They are neutral. And the neutrons and the protons are clumped together in the middle, and then the electrons orbit around them on the outside. Now that I've explained this view, I've explained this model, forget about it. This is wrong. This is not what actually happens. This is a really simplified model that you would give to middle schoolers. So when you take advanced physics, you will learn, and specifically, I'm going to be talking about quantum physics. You will be learning that pretty much everything in this model is not the case. I do not have time to give a deep dive into quantum physics. So I'm going to do just a brief qualitative overview of quantum physics, what it says vis-a-vis atoms. These, this picture of an atom are basically all these balls, all these spheres interacting, orbiting around each other. Quantum physics says that's not the case. Actually, electrons don't behave like particles, they behave more like waves. So the difference would be a soccer ball versus a sound wave. So like a note played on a piano, that sound wave that you hear versus a soccer ball that you would kick. Um, and those two objects behave fundamentally different. You can't kick a sound wave, you can kick a soccer ball. You can, and the way that they travel, the way they move, sound waves disperse. Uh, Soccer balls stay in a single location and move. They behave fundamentally differently. Um, and basically, if you wanted the 3-second summary of all of quantum physics, is that these particles are not actually particles. Protons, neutrons, electrons are actually waves, and they are interacting. Okay. Again, I can't give you the full history of quantum mechanics, the full breakdown, but I'm going to give you a qualitative reason as to why we think slash know this is the case. So this, so in the lower left-hand corner, there's a diagram, and these are called standing waves. So basically, these are the different types of waves that can be produced on, for example, a violin string or a guitar string or any type of string. Uh, when you pluck it, whatever noise you hear is some combination of these kinds of waves. Yeah, these are just the basic waves that occur on a violin, on a string. And that string is one dimensional. So there's only one dimension, it's just length. So what would happen is if instead of a one-dimensional string, you had a two-dimensional object. So how do these waves on a string behave when it's not a string, it's a 2D surface? So an example of a 2D surface is the surface of a sphere. So maybe you take, if the Earth was completely covered in water and all of the waves on all of the oceans around the Earth would be an example of waves that are traveling over the surface of a 2D sphere. Now, the complementary image of these standing waves, so these one-dimensional waves, on a sphere, they look something like this top left image. So the red values would be maybe the peak of the water waves. The blue values would be the trough, so the low point of the value of the water waves. And they oscillate and they change. And basically any wave is some superposition, so some combination of these most basic structures. And there are, okay, I should mention that I'm showing like the first four uh, waves on a string. There are infinitely many of these called standing waves. And then there are also infinitely many of these shapes uh, on a two-dimensional surface. I'm just showing you a subsection. It turns out that these ones are typically the most important. That doesn't, that's a brief aside. Okay, why am I mentioning all of this? Because we're talking about electrons. So let's get back to electrons. Uh, if you took maybe chemistry in high school, you might have seen this diagram. This diagram is a diagram of what are called electron orbitals. So they represent places where it's very likely for an electron to be. Different colors correspond to different electrons. And so there's this line right here. So there's in the middle of this diagram, there's no chance for an electron to be in the middle, but inside these uh, kind of shells, there's a high chance for an electron to be. Um, so if you remember, hopefully you remember a few things from chemistry. If you don't remember the exact details, hopefully these electron orbitals look similar. Um, and if you notice, these electron orbitals are identical, pretty much identical to the way that waves behave on the surface of a sphere. Um, so I found this image by Googling electron orbitals. One Google search. I found this image by Googling, well, these are called spherical harmonics, but waves on the surface of a sphere. So they were completely different Google searches. You would expect to find completely unrelated. They would be unrelated to each other. But this is all going back to quantum mechanics. This version of particles in an atom is wrong. Instead, the particles of an atom, electrons, protons, neutrons, they behave like waves. They behave like sound waves. They behave like water waves. Um, and it's really cool to see. So how am I doing on time? Oh, not great. Okay. Um, I'm gonna skip this picture of a balloon then, if there are questions. Um, and yes, so electron on the smallest scale, particles don't behave like particles, they behave like waves. And then that is qualitatively, you can see that from these images. Um, okay. Now my challenge is to get from that, so how do waves influence the structure of an atom, to how do waves influence the structure of the universe. Um, we're going to have to learn a little bit more quantum mechanics. And the 2-minute summary is basically if you have, okay, this is a way to think about it. If you had a room full of basketballs, you could remove all the basketballs from the room and then there would be zero basketballs in there. That would be, for instance, uh, if atoms were made out of particles, you could remove all the atoms, you could remove all of these particles from a region, and then that region would be completely empty. There would be nothing inside. But atoms don't behave like particles, and you can't do that. So if you have uh, instead, like the surface of water, the surface of a lake has these ripples, has these waves moving through it. You can't just pick up a wave and take it out. They behave differently. Um, and then this is okay, so this is where the analogy breaks down. You could have, a perfectly still lake, but in quantum mechanics, one of the fundamental findings of quantum mechanics is that on the smallest scales, the universe doesn't, excuse me, behave like that. The finding is that on the smallest scales, you can't ever have a perfect vacuum. Nothing can be perfectly homogeneous, nothing can be perfectly flat. If you have a very, very small region of space-time, it can't be looking, there will be some quantum fluctuations, I guess are the technical terms. And these are like sound waves, like ripples on the surface of a lake that just pop in, that just come and go throughout the universe. And I have an animation. So this is a simulated animation of an oscillating quantum field. So just like sound waves propagating through the air, just like water waves propagating over the surface of a lake, this box represents a microscopic portion of empty space. So what you would consider to be a perfect vacuum. There's no particles in here. There's no matter. There's no energy in here. But quantum mechanics tells us that there must be some of these fluctuations. So these orange regions, these blue regions correspond to uh, like local particles popping in and out of existence, um, local fluctuations throughout the universe that are just like slight small ripples on a wave. Basically, the thing to take away is that quantum mechanics dictates that on the smallest scale smaller than an atom, the universe behaves like a wave, behaves like a sound wave. It behaves like these waves. And you cannot have a perfectly flat surface. There will always be these tiny, again, these are all smaller than an atom. On scales smaller than an atom, you will have these quantum fluctuations. And these are, cosmic waves, waves in the cosmos, in quantum fields. Okay, now I just have a few minutes left to get through and connect this to cosmology. So this is a standard view of how the entire universe evolves in time. So hopefully you've heard of the Big Bang, inflation. Basically, the 2-second summary is that everything around us, everything here on the present day, uh, was once, if you go back in time, the universe gets smaller and smaller and smaller, and it's closer and closer together. And at the Big Bang, okay, I'm gonna brush over a few topics, if a few caveats. Yeah, okay. So with a few caveats, at the Big Bang, all of the matter, all of the energy of the universe was concentrated in a microscopic point. So a point much, much smaller than an atom. It was all concentrated in the exact same infinitesimally small region. So that is shown right here. For some reason, they have it glowing white, but there's just a tiny pinprick, an infinitesimally small dot that contains all of the energy of the universe. And what happened at the Big Bang was this rapidly expanded, or this happened during inflation. And then the big, okay, there are some caveats that I'm rushing over. But during inflation and the Big Bang, this tiny region expanded and it grew to the size of a universe in very, very little time. Okay, that leaves a really fundamental question. Something doesn't quite work with this model. And that is, okay, I'm going to go a little bit over time. I'm sorry. That is, okay, all the matter in the universe came from the same location. So that means that the matter and the energy that is currently forming the Earth, that currently makes up the Earth, and the matter and the energy that is currently forming Mars came from the same location. So, how is it possible that if they started in the exact same configuration, they started in the same place, infinitesimally small place, uh, homogeneous, infinitesimally small place, how is it possible that they evolved separately? How can there be two distinct objects if they came from the same place? And they evolved in the same way. You know, physics is just physics. They underwent the same physics. They've been evolving for the exact same amount of time. How can you get one bit of this matter became the Earth, one bit of this matter became the Mars, and for that meaning, for that matter, how can you get some of the matter to become a sun, some of it to become a black hole, some of it to become this galaxy, that galaxy? I hope that you see the question I'm trying to pose. Um, which is, yeah, if everything came from the same infinitesimally small region that was homogeneous and evolved in the same way with the same physics, why are there any differences at all? Why isn't the universe completely flat, completely homogeneous? Just like um just like blended soup or something like that. It should look the same. It should be the same everywhere. The answer, if you can guess, is these quantum fluctuations. So what we know is that on this small scale, on the tiny, infinitesimally small region before the Big Bang, uh, there must have been some quantum fluctuations. When I say fluctuations, that's another word for waves. So these quantum waves uh, dictate that the universe, even on infinitesimally small scales, couldn't have been homogeneous. Um, and what happens is, as the universe, so at this, at the Big Bang, at the infinitesimally small region, there were some slight differences that were caused by these quantum fluctuations. And these quantum fluctuations, again, they're on the scale of an atom. They're minuscule, they're tiny. You'd never be able to see them. You'd never be able to interact with them. But during inflation, those tiny, tiny waves, those tiny fluctuations expanded along with the size of the universe. So what became tiny little perturbations in a quantum field, quantum waves, was stretched along with the entire universe, and they became much larger scale perturbations. So then you would have some regions of the universe were slightly hotter, some were slightly cooler. Some had a little bit more pressure, some had a little bit more less pressure. Um, and the regions that had were more dense, so the regions where there was a slightly more mass, they had a slightly stronger gravitational force, gravitational pull. So they pulled in more matter. And then those regions got larger, they got bigger and they got stronger, or they got more massive. And then that technical term is that seeded the large scale structure that we see today. So the the quantum waves produced some regions that were a little bit more dense, and those regions evolved to form galaxies today. And the quantum waves produced regions that were slightly less dense, and those regions evolved, and they are the gaps that we see between galaxies. Um, for the sake of time, I'm going to skip this slide, but okay, I'm gonna say one word about this slide. Um, this is the light that was produced in the early universe. So if you look back, uh, if you look, and this is real data, so this was collected with a telescope. So these quantum waves produced regions that were slightly hotter and slightly cooler just after the Big Bang, and the regions that were slightly hotter um, produced photons, and these regions produced photons. They're hot, they have a lot of energy, they're producing a lot of photons, and those photons, again, that's how we learn about the universe around us. They traveled throughout the cosmos, and we can see them today. So this is called the cosmic microwave background. Um, really quickly, what it is that these are the quantum fluctuations of the early universe. So I mentioned quantum fluctuations, quantum waves happen on the smallest scales smaller than an atom. I said earlier that you would never be able to see these quantum waves. That's actually kind of a lie. This image is, it's not an image of quantum waves, but it's an image of the effect of quantum waves. It's like a one-to-one correlation, pretty much. Um, and this is the cosmic microwave background. So this is coming from all around us. These photons are uh, hitting us from every point all around us. And yeah, so this is what it looks like. And these are what literally quantum waves look like, quote unquote. And then, so some of these regions were slightly denser, some of these were less dense. That evolved into what we see in the current day. And what we see in the current day are there are regions where there are a lot of galaxies, and there are regions where there aren't that many galaxies. So this video is what I mean whenever I say large scale structure. Every dot that you see is its own galaxy. So a single galaxy, remember, contains between 100 to 400 billion stars. So all of these single dots are individual collections of billions of stars. And you can see it's not random. There's some structure. There are these it's often referred to as a cosmic web. Kind of looks like tendrils or spider webs that are these regions where the galaxies are denser and there are regions where they're less dense. Okay. To take it all home, to wrap up this section of the talk, we're talking about waves. And specifically, what we now know is that atoms don't behave like particles on the smallest scale. The universe does not behave like a collection of particles. It behaves like a collection of waves, like sound waves or like waves on a water. Um, and this gives structure to atoms. It gives structure to everything around us physically, the table that we're on, the seat that you're on. Um, and then, and these are on microscopic scales. And inflation, so cosmology tells us that in the beginning of the universe, everything was in a very, very small microscopic region that then expanded. Inflation tells us this. And that means that the quantum waves that that were present on the microscopic scales are what create the large scale structure that we see all around us today. They evolved forward so the CMB shows slight differences in energy and pressure. Those slight differences in energy and pressure evolved into this large scale network of galaxies that we see today. And this all comes from waves, wiggling things, wiggling jello. It's the exact same thing as sound waves. The exact same physics of why, major chord sounds pleasing, is the same physics that lets us learn about the universe around us and also gives structure on the smallest scales and the largest scales to everything. Uh, and with that, I'd love to stop for questions. I'm going to stop on this slide. I'm going to continue sharing my screen just in case there are any questions related to specific slides. Okay. Someone asked, how do you detect the gravitational waves? That's a great question. Let's go back. Yes, so electromagnetic waves, they physically what they do is they change the strength and the direction of the electric force. And you can detect that pretty easily. Gravitational waves, it's a little bit more theoretical. For the sake of time, I didn't really talk about it. But what a gravitational wave does as it passes is it stretches this fabric, this medium, which is often referred to as the fabric of space-time. So if you haven't heard this before, it's going to sound a little crazy, but physically, what happens is when a gravitational wave passes, it stretches and squeezes all objects. So physically, distances get larger and they get smaller. So again, these gravitational waves are passing through us all the time. They're constantly all around us. They're really, really small, but they physically stretch and compress objects. So if you had a meter long stick and you were measuring its length, as a gravitational wave passed, that meter long stick would get longer and then it would get shorter. So that's the wave. So as the wave passes, that's the effect it would have. Um, and it literally increases in length and it literally decreases in length. Uh, the amount is minuscule. It's tiny. It's a tiny fraction of a thousandth of the diameter of a proton. So it just gets a tiny, tiny bit bigger and a tiny bit smaller. Um, but the way that we detect it is by measuring the distance. They have a really long, um, okay, this is a very simplified explanation, but they have a long rod and they measure its distance, and when it increases in distance, they detect it. How do these waves affect human beings? They do not. They will increase your height by a billionth of the diameter of a proton. So they are not detectable. They will not they I guess they technically do stretch you, but they wouldn't produce any forces. So it wouldn't even feel like you're being stretched. But that's an aside. They will make you so they do okay. They affect humans by making them smaller or taller by a billionth of the diameter of a proton. Such a tiny, minute amount is why it took them so it took us about 100 years to directly detect these gravitational waves because they're so small. Their effect is so small. But yeah, sounds crazy. But yeah, objects literally get bigger and smaller. Okay, another question. So 100 years between being proposed and being actually observed, was that due to not knowing how to or not having sufficiently sensitive instruments with improved sensitivity will we be able to detect the gravitational waves from small objects, example planets around stars? It was from not having enough sensitivity. Excuse me. Um, yes. So what they had to do is, yeah, they took a rod and they had to detect when it increased in length by smaller than the fraction of a proton. Um, so this tiny, minute change that you could never hope to see with the naked eye it's a feat of engineering that they were able to do this. Um, and if you have maybe more specific questions, I can talk about how they do that. But yeah, it's an incredibly difficult scientific task to undertake. So it took 100 years for us to build up the engineering and the technology required to do it. With improved sensitivity, will we be able to detect the gravitational waves from small objects, example planets around stars? So Yes. Well, the short answer is yes. As we get better and better sensitivity, we will be able to detect gravitational waves that were made by smaller objects, smaller and smaller. Um, and I guess I don't know enough about the sensitivity that would be required to see a gravitational wave from a planet around a star. Um, Something to keep in mind is that the strength of the wave is dependent on the smallest object. So this animation has two black holes, so it has two really, really massive objects. If you had one black hole and one really, 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 really small object, even though it's determined by the smaller object will cause the gravitational wave to be very, very small. So if you had um, two small stars, maybe you'd be able to see that wave, but planets are just so much smaller than stars that that would be very difficult to detect. But yeah, I hope that that answers the question. Theoretically, yes, but we would need very good sensitivity to detect basically the gravitational waves emitted by Jupiter traveling around the sun. I don't know how many decades we are away from that we are, but many. Can you comment? Oh, yeah, thanks. So Seth just plugged LIGO. LIGO is the Laser Interferometry Gravitational Wave Observatory. That is uh, the tool that was used to directly detect gravitational waves in 2015. If you'd like to learn more, you can ask me questions or do that. Can you comment on the work measured by Laser Interferometry Gravitational Observatory, LIGO? Oh yeah, I can. Um, so the I in LIGO stands for interferometry, and I'm gonna look up an image of interferometry. Oh no. LIGO interferometer. Okay. Can you guys see my screen? Okay, here we go. Can you see this image? Seth says yes. Okay. This is very simplified view of how LIGO works. Basically, you take one laser beam and you split it into two, and you send one of these beams down one long tube and one of these beams down another long tube. So I said, how do you detect gravitational waves? Um, if you have a very large rod, very large um, tube, as a gravitational wave passes, it will physically get longer and smaller. So you have to measure that. It turns out it's pretty much impossible to directly measure a single rod getting longer and smaller. But it's actually quite easy. Well, I shouldn't say quite easier. It's much easier to detect the difference in length between two arms. Here's maybe a better view. This is what I'm talking about. So this white tube that goes off into the distance is one arm. This white tube that goes off into the distance is another arm. They're both 4 kilometers long. They're perpendicular to each other. They're at right angles. Um, so what you can do is you can measure the difference in length. So you set these two arms to be the exact same length, and then you measure the difference between those lengths. So you would expect it to be zero, but when a gravitational wave passes, what happens is one arm will get longer, and because the other arm's at a 90-degree angle, it'll get shorter. So I don't know if you can see me, but something like this, which is a very fun dance move. It's hard not to feel silly. But yes, because they're at perpendicular angles, one will get longer, one will get smaller, and it's that difference in length. So it's very hard to directly measure a single arm getting longer or smaller. But with this setup, you can measure the difference. Basically, what the setup does is it splits a single laser beam into two streams. One goes down one end, one goes down the other. And when they meet back up, if they travel the exact same distance, there will be uh, they won't have changed at all. So if they travel the same different distance, when they meet back up, when they're combined back up, it will be as if nothing happened. They will look the same as when they were emitted, but in here you can see there's some slight difference. Okay, that was hard to explain. I'm going to do a GIF. Yeah. Does this make sense? Is this too fast? So the greater the difference in length between these two arms, the stronger the pulse at the end. Let's see if there's a better shorter GIF. Okay. I hope that makes sense. I also hope that makes sense because I can't see the chat. But yeah, there are lots of different ways of detecting gravitational waves. And oh, I would be remiss to not mention, look at this. More waves. Everything's waves. To detect gravitational waves, we use light waves. And yeah, which is just why they're so important. Uh, the difference in length is a fraction of a diameter of a proton. Yeah. Um, yeah, I believe it's like a thousandth. Oh, there's a big difference between a millionth and a thousandth, but it's very, very small. A millionth the diameter of a proton, or a thousandth the diameter of the proton. It's one of those. Okay, great. Any other questions? These are all great questions.
I should mention to the group that someplace on our YouTube channel, Eileen O'Donoghue has an entire talk on LIGO, um, which is fascinating. Takes us underground, shows us some of the uh, facility, the animations of the actual facility and so forth. So I'm going to try to find that. It's going back a little bit, I think, into maybe even pre-COVID,
Hmm.
or during COVID at very least. So I'll see if I could find that, and maybe when I post this video in the next few days, I'll include that link to that video as well, because it's all sort of tied up into the same conversation.
We had another question. Is that because the wavelength is so short or because the signal is so different, distant? Um, I hope I'm going to interpret that question correctly. But the so objects are stretched by such a small amount. It's mainly due to the fact that the gravitational force is just inherently very small. Um, so even if you were very, very close to these merging black holes, the effect would not be that large. Okay, like if you were right next to the co-orbiting black holes, would the stretch shrink be just as small? It would be slightly larger, but it would also be very small. So if you were right next to the black holes, you might be stretched by, half an amount, like half the diameter of a proton, which is quite a lot. That's a lot. Half the diameter of a proton. But then if we're many, many light years away, so we are stretched by a thousandth, or in some cases, like a millionth the diameter of a proton. Um, I hope that that answers your question. I should also say, I said that if you were right next to the black holes, you would be stretched by like half the diameter of a proton. I'm making that figure up. I'm not a, but you would be stretched by a very small amount. Don't quote me on half the diameter of a proton, but it's still a microscopic amount for sure, smaller than an atom for sure. And oh yeah, and the reason for that is just because the gravitational force is quite weak. Um, if you yeah, so if you have two electrons Those both have a negative charge that repels each other, but electrons also have mass. So they have the gravitational force attracting each other. But whenever you talk about two electrons, they will never attract each other. You don't even talk about how they have a gravitational force pulling them together because the electric force is just so much stronger. The electric force, which is in that case pushing them apart. That, yeah, when you talk about electrons, you don't even think about the gravitational forces between them because gravity is a very, very weak force. So its associated wave is likewise very weak. The effect of that wave is very small. Hopefully that makes sense. All right, cool.
All right. If that is the uh, some of the questions, and again, our uh, this video will be posted on our YouTube channel, and you'll get a link to that if you subscribe to our email list. And I'm going to put a couple of links in. Here's just for everybody's benefit here. Here are some links that may be helpful: our website, our phone number, email address, Facebook, and our YouTube channel. If you visit our website at AdirondacSkyCenter.org, at the very bottom, there's a place to subscribe to our email newsletters that come out weekly and occasionally more often when there's a special event, like you may have gotten one tonight for this talk. And but in that, you'll see the link for this as in addition to the video for this, you'll see links to our previous videos on our website. But you can visit our YouTube channel for all of our Cygnus series going back, geez, way back to, I want to say June or so of 2020, really when we kind of pulled the trigger on that due to COVID. So, Simon, this is a great talk. I mean, just based on the comments and the questions, this is not to be, you know, uh, trite here, but this is a big topic, you know,
Yeah.
and there are so many little pieces to this that you covered nicely, and I appreciate it. An overwhelming topic, really. We'll be doing more of these. Simon will be doing more of these. I think he's posted his email address directly in there. If you have any questions for him, feel free to email him directly, and stop in and visit us on Park Street. Um, Great job, Simon. Thank you so much for putting this together. We'll be back here in a month from now. You can check out our calendar on our website under Cygnus Series. So with that, thanks again, Simon. Thank you all for joining us tonight. And as always, we look forward to seeing you at our next presentation. Thanks and have a good night.
Great. Thanks, everybody.